All right. Hi, I'm Albert Magyar, and I'm a grad student at UC Berkeley. I'm one of the people who's going to be angling for Chris's desk in 2 weeks. And this is about some work that I did this summer with Don Stark at Google. And it's about how you can get easy custom RISC-V cores through aggressive design reuse. And I think a lot of people have checked out the Rocket chip repo, thought, this is great, we have a well-validated RISC-V implementation, it is feature complete and has been extensively proven in silicon and boots Linux, and start on this upward ascent. Of course, we all know Rocket is not a rocket, it's a train, and then they get to the phase of, okay, how do I turn this thing on? And if they start to notice a little bit of a mismatch, an impedance mismatch with what they want to do, or difficulty using it, then they might think, should we start from scratch? And they might even just go all the way down in productivity and completely launch on a complete re-implementation effort. But I think that regardless of what changes need to be made, and regardless of whether the core should be in a completely independent generator, there is a lot of good structure and independent components in Rocket chip that can be used in almost any application through customized reuse. And so part of this is addressing why are there so many RISC-V cores, and this is a good thing. And there are good reasons, which is if you have a slightly different socket that your core inhabits, the microarchitecture might be heavily influenced by that, and it may be easier to completely tailor the microarchitecture to that than to adapt it to retain good performance if you don't have instruction caches or if you have a slow bus architecture. And there's a perennial theme in these open RISC-V implementations of making tinier and tinier cores with lower and lower area at some IPC and clock rate hit. And of course, if the open source project that is available to start with that's well validated is kind of over-featured and for SMP, Linux, all these things, it's tempting to think, okay, well, I don't need something with all those features. But then there are some less good reasons, which of course there's always not invented here. And I work on Chisel, so it always makes me a little sad to see fear of Chisel, but there is always a little fear of Chisel. But there are some big pitfalls to this, which is, I think, one of the most telling things that I've ever seen about this is in the literature about RISC-V formal, the most commonly encountered bug, I think, was failing to zero the LSB of JALR targets. And these are the far corners. And if you think I'm doing something custom and interesting, I'm going to validate the custom and interesting things that I'm doing, it's more likely that you're going to get those special sauce things right because you're going to test them. But then these very deep, far corners are well validated in Rocket and now better validated through RISC-V formal. And why throw away these things when they're pieces that you might never even hit in your test suite? And the other thing is that under a, up till now, unfrozen privileged architecture, a lot of open source implementations have lagged behind or died off because of kind of disparities with the current direction of the privileged architecture. And I think that design reuse can be totally pervasive in standalone cores, regardless of the implementation language of the overall SoC project. And the key really is just not reusing too little or too much. This is kind of similar to the presentation about the base jump DNA. There is a lot of good DNA in Rocket, and it's built from simple, well-defined subcomponents. And at the top level, for an in-order core, it does hit very high IPC for a shallow pipeline in-order core. And most of the complexity comes from either things like that, like branch prediction or non-blocking caches, or from the Rocket chip generator, which has aggressive parameterization going both up and down the design hierarchy, coherent caches, network on chip, and a very flexible generator that supports pretty much every possible parameter. But instead of going from the top down and making changes, if you reuse this, if you reuse these components, you can build a microcontroller core. As Chris has repeatedly shown, you can build a fast out-of-order core. And you can even do this without building your top-level project in Chisel or reusing the Rocket chip generator at all. And in this way, this is kind of a deviation from how Zscale and Boom work. But by stitching together these reusable rocket components, more than just getting design reuse, you're also getting a good look at the validation of things that you might not test in your particular implementation because they aren't of critical importance to the tests that you want to get running quickly. And key to this are kind of what I think of as the big three components, which are the CSR file, the decoder, and the RVC expander, because throughout an incredibly broad range of relatively simple out-of-order implementations and almost all in-order implementations, it's hard to imagine microarchitectural deviations big enough that would make these not practical to use in some parameterization in a design. The decoder provides largely microarchitecturally agnostic signals, and the RVC expander is defined in a kind of functional way of owing in part to the design of the RVC extension. And the CSR file has more lines of code than most of the simple open source RISC-V implementations because it really actually is fully compliant with the 1.10 privileged architecture. And so this kind of pulling these things together, I was able to make a new RISC-V core IP, Bottlerocket, which is a classic three-stage pipeline. This is very similar to Zscale. It's kind of like almost like a Zscale 2.0. And it has separate fetch and data memory peripheral buses, implements RV32 IMC, and has a constant time multi-cycle multiplier and divider. It implements the privileged architecture 1.10 with machine user privileges, physical memory protection, and custom interrupt extension. It has enhanced support for internal and external clock gating across multiple synchronous domains. And it has a top-level generator that's only 10 or 20 lines of chisel and has all the useful parameters for that kind of core and produces one easy-to-connect tile, or it can produce the individual big three blocks for dropping into a Verilog design. And quantifying reuse, this kind of ignores some of the ancillary blocks in the core complex, but the new core is 14.5% of the overall lines of code that get reused from Rocket Chip, and it implements a completely different microarchitecture and socket interface for the CPU. And again, CSR file is twice as big as all of the code required to write a new core using Rocket components. And it has full support for Sci-Fi debug spec mandatory commands. It has access register, halt control, single step. It also has system bus access and a custom debug module and JTAG device transport module. And kind of really inspired by how common these bugs were, I included the RVFI formal interface and trying to get that going, but I am relatively inexperienced with formal verification, so I'm moving forward with the monitor first. And it has native and debug breakpoint support and a programmable external interrupt controller for any number of external interrupt lines. And again, very vanilla three-stage pipeline. And the Bottlerocket tile, this core sits attached to buses for instruction and data movement and has the JTAG debug transport module and a programmable interrupt controller programmed over a local MMIO bus. And again, this reuse delivers. It kind of takes you from thinking, okay, maybe Rocket doesn't fit the box exactly, and instead of taking months to start from scratch or adapt something, gets you to chip-level integration in weeks instead of months. And a lot of this is due to the power of Chisel to allow you to aggressively reuse designs. And the current status, Google is a big company, so the open sourcing effort is underway, but the integration with RISC-V formal, I'm very excited about that, and I'm trying to get the tandem execution with the monitor running quickly. I've been using the RVFI interface as a trace port for debugging as well. And I want to leave a little extra time, but questions will be during the break, and I'll be around, and yeah, I'll yield the time to the next speaker.